Well, hey there, kiddos. We are going to talk about some more stuff about systems today. Your notes, there's an example at the top with the pictures of the paintbrushes and stuff. We're going to skip it down to here where the definitions are. We're going to talk about some definitions, and then we're going to talk about some things about systems. We're still doing an introduction. So a system of equations is two or more equations containing two or more variables. Up until now, every time we have solved an equation or looked at an equation and tried to find a solution, that equation has involved one variable, and we solved it by doing inverse operations, and that's all we did. Now we're going to have two different equations, and those two equations are going to have two variables, and we're going to have to solve and find both of them. A solution to a system is the point where the two lines cross on a graph. And we talked about that on your video over the weekend, and you found where it was the intersection point. And so that's what a solution is. And since we're talking about a solution being where two lines intersect, then we have to talk about how many types of systems there are. There are three. The first type of system is the one you'll see the most often. You'll be the most familiar with it. It's called an intersecting system, and that's where the two lines just intersect one another. And because they intersect in one point right here, then they have one solution. Intersecting lines always will have different slopes. If they don't have different slopes, then they are not intersecting, and we'll talk about what, if the slopes aren't different, what that means. But intersecting lines will always have different slopes. So if you're looking at the equations, you compare the slopes. Different slopes means they intersect. It means one solution. Another type of system is when you have a parallel system. And y'all should know that parallel means that you have two lines that never ever intersect one another. So they run parallel and they're never going to touch. And since they never intersect, then they have no solution. And if you'll remember from first semester when we talked about parallel lines, we talked about the fact that parallel lines have the same slope. And that's how you'll know two lines are parallel. There's no solution. They'll have the same slope. The third kind of system is called a coincident system. It's when the two lines are really not two lines, but they're the same exact line. And so when you graph them, they graph one right on top of the other, and so they intersect everywhere because they're the same line, so they're always intersecting. And so when this happens, we say that there is infinite solutions. And the way to tell if two lines are going to be coincident is they have the same equation. Every single part of their equation is identical, and that's how you'll know if there's infinite solutions. So sometimes you don't have a picture, you just have an equation, and the question is, how many solutions is this going to have? And here's how you tell. We have to look at the slopes. Well, the only way to look at slopes and compare slopes is for all of our equations to be in this form, slope-intercept. Because then we can compare the m values and see, are they the same, are they different, what's up. So number 2 here, the second example, the first equation is in this form. It's y equals 5x. We're good there. The second equation is not, though. The y over here has a 1/5 with it. So I'm going to have to solve for y by multiplying this whole equation by 5. So these 5's will cancel. So I have y equals, and then over here I get 5x plus 35 because I have to multiply both parts of this by 5. So now I can look at my two equations. I got y equals 5x and y equals 5x plus 35. Well, they're not the same equation, so they can't be infinite solutions, but they do have the same slope. They both have a 5 in front of the x. Since they have the same slope, that means they're parallel lines, so this system has no solution, so I'm just going to write none. Number 3, I'm going to have to do the same thing. I'm going to have to get y by itself for both of these. So the top equation, to get y by itself, I'm going to have to add this 3x. So it's going to become y equals 3x minus 1, because I just added 3x to the other side and kept that negative 1. This bottom equation, I'm going to have to divide everything by 6 so that I can get y by itself. And when I do that, I get y equals 18 divided by 6 is 3, so I have 3x minus 6 divided by 6 is 1. And if you will notice, these are the exact same equation now. Now that I have y by itself, they look identical. Same equation means infinite solutions. So that's how we tell. We look at our equations, compare the slopes, look at the two, and see what's the same and what's not, and that's how we know how many solutions it has. Now, to determine if a point is a solution, and we did some of this in the notes over the weekend, but we're going to practice it again. If I want to know if it's a solution, I take the point, the ordered pair x comma y, and I plug it in. And then when I plug it in, I see, does it make both equations true? If it does, then it's a solution. If it doesn't, it's not. So my point is 5 comma 2. So in this top equation, I'm going to do 2/5 times 5, because in my point x is 5, minus 2, because that's what y equals, and it should equal 0 if it works for that equation. Well, 2/5 times 5, the 5's cancel, so I have 2 minus 2 equals 0, and the last time I checked, 0 really does equal 0, so the point works for this equation. Now we have to test the bottom equation. Change colors here so you can tell the difference between what I'm doing. So for the bottom equation, I have to do 3 times x minus y, and it should equal 13. Well, 3 times 5 is 15, minus 2 should be 13. And if I do that math, 13 does equal 13, and so since that's a true statement, it works for both equations, then yes, it's going to be a solution. So let's look at number 7 here. We're going to do the same thing. We're going to plug in our values and see what happens. So negative 2 plus 3 times 2 should equal 4. Well, negative 2 plus 6 does indeed equal 4, and so this point works for the top equation. So that means I have to go check the second equation. So this x now has a negative in front of it. So when I plug in a negative 2 into a negative x, this negative and that negative will cancel, and this will just become a positive 2. Plus y, which is also 2, should equal 2. Well, last time I checked, 2 plus 2 was 4, and 4 does not equal 2. Since this one doesn't work, it doesn't work for the bottom equation, so no, that one is not a solution. It has to make both of them true. So now let's just talk about writing some equations. We're going to go from some words to some equations, and then that's all we're going to do. We're not going to solve anything. So number 9, you have a picture here. Robert and Juanita both went and bought fruit baskets, and in those fruit baskets there were apples and pears. Okay, and then in the pictures it tells me how much their baskets were. We don't know how much one apple or one pear are, but we're going to write in a system of equations so we can find it. Let statements. That's where you define your variables. I've got apples and pears, so my let statements, I'm going to say let A equal apples. This way, if I choose to use something other than A for apples and P for pears, I'll know which one stands for what. You always have to define your variables. So these are my two variables. A is apples, P is pears. If you wanted to use X and Y, that's fine by me. Just tell me which one is which. Then I'm just going to write an equation for each basket. This basket has 1, 2, 3, 4, 5, 9 apples, and 1, 2, 3, 4, 5 pears. And it tells me in this little box that that cost $5.25. That's the equation for that basket. This basket has 1, 2, 3, 4, 5, 6, 7 apples and 4 pears, and it cost $4.10. Those are your two equations, and so you see we have two equations and we have two variables. And starting tomorrow, we'll start talking about how to solve these and get the answers and find out what they are. But for now, this is all we have. So look at number 10. A breakfast menu lists 2 eggs with 1 sausage patty for $2.23 and 3 eggs with 2 sausage patties for $3.76. Set up a system of equations to determine the cost of 1 egg and 1 sausage. So we're going to let X equal eggs, and we're going to let Y equal sausage. I didn't want to use E and Y. There's nothing wrong with the letter, or E and S. There's nothing wrong with the letter E for eggs, but using S for sausage, S tends to look like a 5 sometimes. It's real easy to get confused, so I don't like it as a variable. So here are my variables. My first sentence, 2 eggs and 1 sausage is $2.23. So that's my equation. 2 eggs plus 1 sausage is $2.23. The next one says 3 eggs and 2 sausages is $3.76. So 3 eggs, 2 sausages are $3.76. So those are your 2 equations. Now questions like number 11. Number 1, I would not set up number 11 as a system of equations and solve it if I were doing this problem for real. I would solve it a completely different way. But we do need to know how to set up the system, because sometimes we run across a question, it's multiple choice, and it's like which system matches, and you've got to know what is what. So I'm gonna show you the system and how to set it up, and then I'm gonna show you how I would do it so you can see both. And then when we actually solve, I'll show you. So I have a rectangular flower patch that has a perimeter of 48 feet. The length of the garden is 2 feet more than twice the width. So we want to set up a system that will determine the length L and the width W of the flower patch. Well, they gave us the variables in the problem, so the let statements are easy. Let L equal length. Whoops. And we're going to let W equal width. And yes, you always need to write your let statements. This way you know what variables you're using and what they stand for. The first thing I know is that I have a rectangle. So over here, I'm going to draw myself a picture. So I know it's a rectangle, and I know I'm dealing with the perimeter. And so I'm going to go back to junior high, and I'm going to try and remember what the perimeter formula is for a rectangle. And what I remember is that that formula is 2L plus 2W, and it equals the perimeter. But up here it tells me the perimeter is 48. So there's my first equation. For some reason, when writing a system, this is the tough equation to come up with. I think it's because we have to try and remember the formula, but this is the equation that kids always forget, is the perimeter equation. The second one's not so hard because it's given to you in the words. It says the length of the garden is 2 feet more than twice the width. So the length is 2 feet more than twice the width. This one you all kids almost always get. You'll get the 2 plus 2W and will be good, but we will forget to write it as an equation. This would be the system. How I would set this up if I were really going to solve it is that I know that the length is 2 plus 2W because I got that from the words. And if that's the length, then these are the width. And I would just add them up and solve. And we will talk about that when we talk about solving. But this is the system that you would have to use. So let's do this last one, and it's a very wordy problem, but you're going to run across them, so we should talk about it. So you were collecting tickets at a football game. Reserve seat tickets cost $4 each, and general admission tickets cost $3 each. So I have 2 kinds of things. I have reserved and I have general. So here's what we're going to say. We're going to let X equal reserve seats, and then we're going to let Y equal the general admission. So after the game is over, the turnstile count, that's that little thing that you walk through when you go into a game or a concert or whatever, shows that 1,787 people paid admission. You count a total of $5,792 from the sale of tickets. You are ready to leave for your post-game date when your boss says, by the way, how many of each kind of ticket were there? Rather than spending half an hour sorting and counting all the tickets, you decide to just use algebra. So we're going to set up a system. Okay, so here's what I know. I know that there were a total of 1,787 people. Well, those 1,787 people bought reserve tickets, and they bought general admission tickets. And it made this many tickets total. I also know that the reserve seat tickets were $4, and the general admission were $3, and my total amount of money was $5,792. So that would be your system. Whenever you're dealing with a problem like this where you've got a total number of items or people, and then you have a total cost of those items, you have to have 2 equations, one for the total of the items and one for the total price. And so that's how you have to look at it. So this is my total items, this is my total cost. So we will practice this when y'all come to class tomorrow. I will see you then. Have a good rest of your day.